essentially, question number 6 talks about a random variable x whose CDF fx is provided here. It basically has three ranges: x greater than equal to 1, 0 less than equal to x less than 1, and x less than 0. So 0 and 1 are points of potential discontinuity of capital Fx. We'll have to check them. And the options talk about probability x greater than 0.5, variance x, and expectation x. So basically, we need to find out these three quantities. So first, in these cases, we start off by obtaining the points of potential discontinuity, that what is the probability at those points. Like, for example, the points here, as I mentioned, are 0 and 1. So we will find probability x equal to 0, which is f of 0 minus f of 0 minus in this case, which is, I have just simply substituted x equal to 0 in these two values. Let me open the question once. Yeah, so f0 minus is 0 only, and f0 is just 1/4 plus half into 1 minus e to the power minus 0, which is basically 1. So this part cancels out, and it's just 1/4. So probability x equal to 0 is 1/4 minus 0, which is 1. Probability x equal to 1 is f of 1 minus f of 1 minus. I have just simply substitute the values within the required ranges, and it also comes out to be 1/4. And then I have differentiated fx over the suitable ranges, that is x greater than 1, 0 less than x less than 1, and x less than 0. And I've obtained the values of fx in the point it is continuous in this upper part. And here, along with these two parts, I have simply added the points 0 and 1, which are points of discontinuity. So x is essentially a mixed random variable, which takes up positive probabilities in discrete points 0 and 1, and positive probabilities in the continuous range x greater than 1 or 0 less than x less than 1, and 0 other. So in these cases, we need to go for checking the options. First, we check probability x greater than 0.5, which is simply 1 minus probability x less than equal to 0.5, which is 1 minus f 0.5. We simply substitute x equal to 0.5 in this form, and we obtain this 1/4 plus e to the power minus 0.5 by 2, which comes out to 0.55. And expectation x is x into probability x equal to small x in the discrete point, that is 1 and 0, and simply integrating it from 0 to infinity in the range 0 to infinity, x into fx dx, since fx is e to the power minus x by 2 in this range. So that comes out to be half of gamma 2 plus 1/4, which is simply 3 by 4. So we can check that option C is the only correct option. And we don't need to check the variance of x, since in option B, it says that expected x is 1 by 16, which is obviously not true. So B is not true. And in part D, it says x greater than 0.5, that probability is 0.66, which is again not true. So D is obviously not true. So by this method, we can actually avoid the calculation of variance x, which happens to be the case with the options. But if obviously variance x was an independent option, we would have to check it separately. Next question talks about two urns, U1 and U2. U1 is a very well-known problem in statistics, and urns and the balls problem. U1 contains 3 white and 2 red balls, and U2 contains only 1 white ball. A fair coin is tossed. If head appears, a ball is drawn from U1 and put into U2. If tail appears, 2 balls are drawn from U1 and put to U2. 1 ball is drawn from U2. And we need to find the possibility or probability that head appeared on the coin, given the drawn ball from U2 is white. So obviously, this is another classic example of Bayes theorem with a twist in the sense that in Bayes theorem, we usually deal with 2 events. Here we are dealing with 3 events actually. So the solution is here. So H and T denotes the event that head and tail appears. W2 is the event that a white ball is drawn from U2. W and R denotes the color of the ball drawn from U1. So probability H given U2 is simply this expression, a very well-known expression from the Bayes theorem. So I'm not going into that, which comes out to be this. From this, since probability head is equal to probability tail, is a fair coin. So we can just cancel it out from numerator and denominator. So this is the expression we have with us. And now we have to compute these probabilities. Probability y2 given head is probability y2 given white comma head, that is a white ball is drawn from urn 1 and head appears, into probability white given head plus the same thing with the red ball. Excuse me. So I've simply substitute the probabilities that here it says that in urn 1 there are 3 white balls and 2 red balls. So obviously probability white 1, the W1 is 3 by 5, and W2 given W is that the same way with 1 white ball inserted to W2. In U2, I mean, there already 1 white ball. Adding another white ball means the probability of drawing a white ball is simply 1. And that it goes the same way with the red balls. So this is probability y2 given head. And probability y2 given tail, there are 4 cases, because here we're actually drawing 2 balls from the first urn. So the cases can be found out similarly. Probability y2 given 2 whites common and tail into probability 2 whites given tail. And the 4 cases I have some written them down. 2 whites, the first white, second red, first white, and the 2 reds. And I've simply put in the 2 probabilities, that is the probability of drawing 2 white balls to drawing 2 balls without replacement from the urn, and what happens after adding of the 2 balls. Say for the first one, adding 2 white balls means there are 3 white balls in the urn U2, and obviously the probability of drawing a white ball from the second urn is 1. And similarly, you can find out the other cases. And the second and the third case are essentially the same. So this comes out to be 11 by 15, and this is 4 by 15. So our required probability is probability head given W2, which is this 4 by 5 by 4 by 5 plus 11 by 15, which is 12 by 23. So let me get it back. So D is the correct option.
Hello guys, welcome to Cheenta School of Statistics and Data Science. We are a team of extremely passionate teachers, researchers, and statisticians from the top universities of India and USA. Our mission is to help you curve your career in statistics, data science, and machine learning. How do we do that? Number one, we help you build your foundations. We achieve that by making an optimized plan for your learning journey. Number two, we help you prepare and ace your entrance examinations in statistics and data science, like IIT MS, ISI Mstat, and CMI MSc Data Science. Number three, we give our absolute best to help you design your career by organizing workshops and certified data science courses. To book a trial class for your preparation courses of IIT MS, ISI Mstat, and CMI MSc Data Science, check out the first link in the description below. If you're enjoying the video, show some love by liking the video and subscribing to the channel. We welcome you again to this passionate community of budding statisticians and data scientists. Let's enjoy the rest of the video. Stay tuned and stay blessed.
The question number 18. So let me just get to the solution. So question number 18, we are denoting the number of white balls in the urn after the TH stage by WT, and the number of white balls drawn in the TH stage by WT dash. Okay. So essentially, after the T minus 1h stage, there are WT minus 1 white balls. In the next stage, we are drawing WT dash white balls. And after that, we will be left with WT white balls. Okay. So WT dash given wt minus 1, that is, there are wt minus 1 white balls after t minus 1 turns, this follows a hypergeometric r comma b plus w plus r comma wt minus 1 by b plus w plus r distribution. Okay, this might seem very complicated, but let me explain you. So one by. So at each stage, we are essentially drawing r balls. So small n, that is sample size, is r. Capital N, the population size, always remains b plus w plus r. And so the proportion of white balls in the urn after t minus 1 stages is wt minus 1 by b plus w plus r. And w1 dash, that is the number of white balls drawn in the th stage, is hypergeometric r comma b plus w plus r comma w by b plus w plus r by the similar arguments. And from w1 dash, you can recursively define the wt dash given wt minus 1. So this expression is essentially for t greater than equal to 2. Now, let us first find out expectation w1 dash. So expectation w1 dash is, as we know, for a hypergeometric small n comma capital N comma p distribution, it is small n comma p. So here small n is r and capital N is w by b plus w plus r, which is w by b plus w plus r into r. And so expectation w1, that is the number of white balls remaining in the urn, is w minus expectation w1. So it is w into b plus w by b plus w plus r. This is a simple algebra, you can do it. So here in the options, we are given the expected number of balls, white balls, over t stages, t greater than equal to 1. And I have obtained the expected number of white balls of the first stage. So in the second stage, expectation wt dash, w2 dash, is expectation of expectation w2 dash given w1 by the law of conditional expectations. So w2 dash given w1 from here follows a r comma b plus w plus r comma wt minus 1 by b plus w plus r distribution. So his expectation is obviously r into wt minus 1 by b plus w plus r. This constant part just comes outside, and this expectation w1 we need to compute, and we already have computed that. We simply put it in the expression, and we get b plus w by b plus w plus r whole square into rw, and expectation w2 is simply expectation w1 minus this conditional expectation. So it's b plus w by b plus w plus r whole square into w. You can observe that even for t equal to 2, it's true. And you can simply extend this by taking in the next stage, you can take expectation w3 dash is just expectation of expectation w3 dash given w2. You can generalize it for any t in a similar manner.